Okay. Kind of testing. Okay. So welcome back. I think we have changed another batch of student here. Seems like different faces from last time. That's fine. So let me remind you that this full screen. Okay. So let me remind you that so this is not a lecture. Okay. So we are trying to go through try to connect some ideas. Okay, in mathematics, and the purpose of this tonight's talk is to like prepare for the language for QM, which we will use. Okay, the vector space, Hilbert spaces. Okay, so the aim of today's talk will be to cover up to Hilbert space. Get the definition of Hilbert space. If we can finish Hilbert space earlier, then maybe we can discuss a little bit about the properties of Hilbert space. Okay. Yeah. So feel free to stop me at any point. Okay, if you want to ask any question. So all right. So let me remind you what we have done last week. So last week basically we introduced two very important definition in maths, which is set and functions. Okay, so what are set? So set are just a collection of elements. So for example, we have a set of participants here. So you are the element of the set. Okay. And functions. So what does function do? So what does function do? So functions typically relate to sets. Okay, functions between sets. So if I give you one element in the domain, you should give me one element in the codomain. Okay? So a function could be many to one, one to one, but it cannot be one to many or many to many. Okay. So if it is one to one, then the function is injective. Okay. So I posted up the notes after the talk, and then I also posted up the somehow lecture notes, not kind of lecture notes, but the note that I compiled. You can read about it because sometimes maybe due to time constraint, I don't choose to present it. But if you have question, you can just raise it up. Okay. Yeah. Anything inside the notes or outside the notes, you can ask. Okay. Because certain definition inside there, I don't choose to present it here, but I choose to put inside the note to make the note more coherent. Okay? But sometimes it's too technical and we're not going to use it, then I will just skip through. Okay. Is that fine? But you can just bring up the question anytime if you like. If you want me to clarify anything inside the note or clarify anything what I said, even want to clarify the thing that I skip, you also can ask. Okay. But for my presentation, I will choose to skip something. But if you want me to catch me, feel free. Okay. Okay, no. Okay. Yeah. So feel free to stop me. All right. So let's continue. So we have a set of things. So what are we going to do with the set? Okay. So what are we going to do with the set? So there's one very interesting phenomenon if we can combine elements inside the set. Okay. So let's define a term called the law of composition. So now we will enter the part of the group theory. Okay, I will use group theory to construct vector space for you. Okay, and then I'll show you some property of vector space. Okay, so let's define law of composition. Okay, sometimes we call it LLC, or sometimes we call it a binary operation. Okay, so from the name, you should guess what is this? What should this thing be? okay, or what are the what are the clue, okay, that the name give you to define this thing, okay? Law of composition. So it's some kind of law. Composition, you want to compose. So when you compose, you need to have at least two things, right? So you need to have at least two things to compose. So that's why there's another name, we call it binary operation. So it's binary, okay? So binary. So what is this? So let's denote it as the asterisk from S cross S to S, okay? So what is S? So this S is a set, okay? So we are going to play things on set, okay? So it's a binary operation on set. So we denote it as the asterisk. So it's a function, okay? So this thing is a function of two variables, okay? Function of two variables. So you give me two things in X, okay? I give you back one thing in X. Okay? Law of composition. So it's a function, all right? Okay, so this is a law of composition. So what's the next thing? So okay, next. So if I taught you how to combine two elements, right? A cross B, okay? How about if I compose the third element? How do I do it? So A compose C. So let me put a question here. So I told you how to compose A and B in X, okay? Question. So how to compose three elements, say X, Y, Z, okay? If you know how to compose two elements. You only know how to compose two elements. Any idea? How do you do it? So you know how to compose two things. So from here, can you guess how to compose three things or not? Idea? Yeah? Okay. So you mean maybe we combine X and Y first, and then we combine Z. Right. Yes. Okay. So this is one way. But there's another way to do it. You can combine Y and Z first, and then combine with X. Does that make sense? So there are two ways you can do it, right? So you could, or you could do X compose Y. Okay, two things. Okay, so this is another thing in X already. So I can compose with Z again. Or we can compose the last two things and then compose with the first thing. Right. So these are the two ways to compose three elements. But there's no guarantee that these two is the same. Okay. So there's no guarantee that these two have to be the same. Right. So we will say that. So we will define another term. So we will say that a LLC, a law of composition, is associative if, okay, if any three elements in your set, okay, this two kind of composition is the same. This is associative. So you could imagine there's non-associative LLC, but usually what we do with numbers, they are associative. Okay? When you add numbers, when you multiply numbers, usually they are associative. There's no order for you to worry about. Okay, when you do addition or multiplication of numbers. Okay. Next, this is associative. Next, we'll call that a LLC is commutative. Okay, so it commute if for any two elements x compose y is equals to y compose x. Okay, so this is commutative. So we have introduced two adjectives for LLC. Okay, a function. When is a LLC associative? When is a LLC commutative? Okay. So can you think of any commutative LLC or not? Addition. Okay, addition of numbers. Commute, right? 2 plus 3 equals to 3 plus 2. Okay. Anything else? Multiplication also, right? 3 times 2 equals to 2 times 3. Okay. All right. So next, very important thing is what we call the identity. Okay. So an identity for LLC on X is an element, usually we call it E, such that for any, here should be any, for any X in X, okay, E composed with X should return X, and also X composed with E should return X. Okay. So the identity element is the one that when you compose with everything, you give back yourself. What is the identity? Does it make sense? Identity doesn't change, right? Okay, so what doesn't change? So the element that you compose. Okay. All right. So does it make sense? So up to here we have three definitions: associative, LLC, commutative, LLC, and identity. Okay. One last definition before we introduce what the group is. So an element X in S is invertible. Okay. So when I talk about invertible, right? So what does it remind you? You learn linear algebra. No? So what's the invertible matrix does? Sorry? Combine. What's the thing that combine? So if M is invertible, then there's a inverse. When they compose, you get the identity matrix. Okay. All right. So similar here. So an element X is invertible if there exists and Y in X such that X, Y give you back the identity and YX give you back the identity. Sorry. Thanks. Okay. Okay. And here we will call Y the inverse of X. And we'll call the inverse of X. So not that I put the here. So what does it mean, the, in English? The means what? Unique. Uniqueness. That one, that particular guy. Okay. The inverse. So you can show that actually this Y is unique. Okay, if it exists. So last week, someone asked about me about how to show something is unique. So how to show something is unique, right? So how to show something is unique? So showing something is unique is I'll say a trick or a normal argument. So how do you show that this pen is unique? How do you show that this pen is unique? You take two similar pen and then show that they are the same pen. Does that make sense? Okay, maybe let's show you this trick since someone is interested. Oh, and inverse of an element is unique if exists. Okay, if it exists. It might not exist, right? For example, the sum matrix is not invertible. Okay, but some matrices are invertible. Okay, so how to prove this? So suppose, okay, so let's call this element x for the moment. So suppose y1, y2 are inverses of x. Okay. And then what we want to show is, okay, so I abbreviate it to WTS, want to show. What we want to show is y1 equals to y2. Okay, so how are we going to show this? Not that. I can start with y1. Okay, so what can I do? I can do y1 equals to y1 composed with the identity. Right? Okay, I can do this. What else I can do? Since E is the identity. And next, how to generate E? I can generate E using y2 because y2 is the inverse of x, right? So in particular, x composed with y2 is E, right? Okay. So what's next? Okay, what else we can do? Right? So we can use associativity. So not that we consider LOC that are associative. Okay, so we can use associativity here. Okay. Use associativity to change the order of composition. Okay, so we have assume associative LOC here. Okay, so we'll get E composed with y2, and E composed with y2 is just okay, so it's unique. So suppose you have two things and then show that two things are the same. Okay. So not that I use again the identity here. So similarly, you can show that the identity of a LLC is unique as well. Okay, if less for exercise if you want. Okay. You can show that the identity of a LLC is also unique. Okay. So this is done. So you can run exercise, show that the identity of LLC is unique. Okay, so I think we are good to introduce group now. It's a group. A group, first of all, it is a set. Okay, it is a set. Okay, it's a set. I will write it as a G, comma, the composition, the law of composition. So it's a tuple. Okay, so you can this composition has to be associative. So that's me. I have a set, and then I know how to compose two things inside my set. Okay, and satisfies how many properties here? So there are two properties. So satisfying two properties. So do you want to guess what the property is, given what we have introduced? So max is like this. So our culture or our logic or our presentation is we define everything we need and then we will use it. Okay, so we have defined associativity, associative law of composition, commutative law of composition, identity, inverse. Right. So how are we going to use this? So we have used associative LLC here. Okay. So the next thing is we want an identity elements to exist. Okay. If it is a group, we want an identity elements to exist. Okay. And every group element is invertible. Okay. So there's all the elements they have their inverses. Does it make sense? So how about commutative? So we will say that a group with a commutative law of composition is called an abelian group. Okay. So it's named after a guy called Abel. Abelian group. Okay. So I think abelian group is more common. Okay, when you learn maths. Okay. So what are the abelian group example? Any idea? Sorry? Numbers? Yeah, what kind of numbers you have? Also, last week we talked about some numbers, right? Natural numbers, integers, rationals, reals, right? Okay. So for example, Z with addition is an abelian group. So what's the identity here? What's the identity inside this group? What's the thing that when you add to it, you get back yourself? Zero. Good. Okay, so the identity here is zero. So everything has, identity as is. How about inverse? Does every element has inverse or not? If I give you an integer n, what's the thing that you add to it, you get zero? Minus n. Okay, so minus n is the inverse of n. Is it unique? Unique or not? Unique, right? Okay. But what we have done just now is we have shown for general case here. Okay, so this is the power of proposition when we prove proposition. Okay, this work for any set. Okay, any set with associative law of composition. That's why mathematicians are obsessed with proposition because we want general statement, not just example. Is it true for other case or not? How like how true, to what extent this statement is true? Right. For different, maybe it's true for different examples, but what's the extent it is true? So to the extent that a set is, as long as you have a set with associative law of composition, okay, then inverse of a element is unique. Okay, right. So this is that. And what else? We can consider addition of rational number as well. Okay. And actually, we also can consider rational with multiplication. Okay, but so I need to be careful here. Does 0 has an inverse under multiplication or not? What's the identity for multiplication operation? 1, yes. So 1 over 0 defined or not? Not defined, right? Undefined. Okay, so here we have to get rid of 0. So all the non-zero rational number from a group under multiplication. Okay, so similarly, you can consider the real number, non-zero real numbers with multiplication. Okay, so these are all abelian groups. Does it make sense? Okay. Okay, so what time is it? Huh? Okay. So any question up to here about definition of groups? Maybe you need to construct one group that is not abelian. What group is not abelian? Yes, matrix multiplication is not abelian. But does it form a group or not? Matrix. How? Does every matrix has an inverse or not? No, right? So how? So what can you do? What can you do? What can you do? Yeah. So you just consider all the invertible matrices. Okay. So the set of invertible matrices form a group. Actually, this is a very important group in physics. This is a GL. This is what we call a GLN. So what is this N here? So these are the N by N invertible matrices. If your physical process is invertible, then probably you need this to describe it. GLN. Okay. Yeah. So how to find the inverses of matrix? You learn in linear algebra, right? What's the method you use? If 2 by 2 is just the 1 over AD minus BC, and then you swap some terms and then add some minus. But in general, how do you find it? Determinant? Not quite right. What's the process? Yes, cofactor is mentioned, right? And yeah, you use the cofactor function to find the inverses. The identity is just the identity matrix. That's why it is called the identity matrix. Okay. All right. So let's see how should we go so far. Okay, sure. Should I discuss this morphism first or not? Okay, maybe we don't talk about homomorphism yet. Let's introduce one important thing for us to go to vector space. So I want to directly introduce you another new notion. Okay, so we have a group, then we have an action of group. Or what does the action of group mean? For action, you want to act on something. Okay, so what's the thing you need to act on? So I have a group, okay, and I have a set. Again, it's a map. Okay, a map of two variables. Okay, so I give you a group element. I want it to add on a set. And then what should I get? Oh, this could be meaningful. I want to see how my set changes. Okay, so it should give me something back inside the set. Again, a function of two variables here. Okay, so of course, it's not a general map we want to consider. So that you have to satisfy some property here. So if I write it as an element form, so I will send gx to g acting on x, okay, which is some x prime here. Such that, okay, so it's not just any function that we want to consider, but there are two, again, two property we want to follow. So first of all is the identity laws. So what's the identity laws? So the identity inside my group should add trivially on my set. You should think that there's no relation between groups and set, right? Why should there be a relation? There could be a different set, again, for group and a set. But I require that the identity element in my group, because to be a group, you have to have the identity elements. It has to act trivially on my set. It doesn't change my set. Okay? Make sense? Okay, so this is the identity law. Okay, second. So again, this is a associative law. So you see that we like associativity a lot. So what is associativity here? So for two elements in G, okay, what can I do? I can compose two elements first, right? Because it's a group, okay, I can compose two group elements, and then I get another group elements, and then I let this element add on my set, okay, as some element in my set. This has to be equals to G prime acting on X first, and then G acting on G prime acting on X. Does it make sense here? Does it make sense? So here is the group element acting on X. You should get something in the set. Okay. Here, so G prime acting on X, you get something in X. Then you take group element add on the element in the set again. Okay. Okay, does that make sense? Up to now. Maybe a bit dry here. So what kind of a group action you can think of it? It's a very daily life thing, right? So actually what I'm talking about here is about symmetry. So a very important example of group action is symmetry. As long as you have symmetry on that, the object you have here, you have a group action, right? So for example here, this bottle here, what kind of symmetry you have? Rotation, right? You can rotate it, and then you get the same bottle back. Okay. So how many rotations you can make? Actually, you can make for every degree, 360 degrees. So if you make a full turn, then you will get back the exact same bottle. So rotation, you can check that rotation from a group. You can, what's the identity inside the rotation? You did nothing, zero, rotate, 0 degree. What's the inverse for any rotation? So if you rotate about the degree of theta, so what's the inverse of it? Just rotate negative theta, right? Okay, so invert that two. So it form a group. And this bottle become my set. Okay, I take a rotation and add on my set. Make sense? Okay, so maybe you think of it. So what kind of element here? So the element you can take is the every particle inside this water, maybe. Right. So if you can draw this water on the R3 plane, then you can have coordinates for all the point inside the water. Make sense? Okay. Okay. So the organizer asked me to stop now. So any question before we go into a toilet break? Any question before we go in? Yes. I mean, this one, left one, yeah. How they compose here? Yeah. So where are they from? They are from group. So inside group, what's the definition? Is yeah. Yes. Okay. Okay. Sorry. Okay. I think I better keep the same notation here. So put the star. Okay. Is it better? Yeah. Okay. Because usually when we talk about this asterisk, right, we think of it as a multiplication always. Because in group there's really only one law of composition. So there's no ambiguity between addition and multiplication, but usually we regard it as a multiplication because it resembles multiplication a lot. Okay, any other question? Which one? This one is correct because G add on X is something in X. So how you combine a group element with a set element, you need to add. Yeah, no? So you combine and add and then add separately is the same. This is the idea of this one here. You combine and then add is the same as you add in order. I cannot just say separately, but in order. Separately in order. Okay. Does that make sense? Yeah. So this is the group, right? Okay. Okay. If no question, then let's take a break until at 02. Okay. If you still have question, then you can ask at the start later. And let's return 802 and for toilet break. Okay. Okay. Yeah. 啊，对对对，你在弄你的想象图，你这边是写我写什么？我刚才好像有看到一些有问题的，但是哪一个？啊，对对对，哎啊，对对对，画错去，改一下，没有这个错，这个错，这个错，这个错，太多 notation 的时候。你的 cos 那个 cos 是什么 ？cos s 啊，cos s。OK，好吧，等下解释一下。我看前面也是有人 cos，但是我有一点 skip 掉，我不懂还是哪里就给这样。OK，等下解释一下。OK。这边这个意思。 就是一个product set。嗯。你觉得我因为已经接触到这个了，其实这个我什么？这个东西在一个但是因为后面这个是一个 matrix，一个对，我觉得是 vector space，对，对，但是这个在更多 structure，就是它是一个 vector space，但是你按这个，是，它是一种 group action 来。我们 open question 有一个其中一个这个题目嘛，所以等一下，你觉得我适合在你 after break 直接看你，还是要 Q&A 才看你？像这样，这种嘛，按这个 question 的话。我们有一个 open question 是这个。等我讲完，对，等我讲完，对，那我讲完，对。呀，我突然突发奇想，那个东西刚跟你讲的时候，是吗？因为如果他们没有，Abelian group 才对呀。肯定他们都是不 Abelian 吧？应该不 Abelian。对啊，因为它是 matrix group 嘛。啊呀，不是 Abelian。对，对，没错。I think should we start again? I think our time is quite precious, so let's not waste more time. So 今天 raised a very good question. I purposely skipped. Thanks for catching this. So I put here G multiply with X. What's G multiply with X? If I write something like this, so this little g and little s is an element here. Can you guess what is G cross X here? So what is G cross X here? So G is a group, in particular is a set. S is also a set. But what does it mean by a set multiply a set? Usually when it is when it is a set, when it's not number, we won't say it's a multiplication. Usually we say cross. Okay, G cross X is just a cross, not multiplication. So where's G cross X here? Any idea? Is it an operation? Is it an operation? Maybe not quite. Not quite. So it's another set. So to describe a set, what do you need to do? You need to tell me what's the thing inside there. What's the element? So describe a set by elements. So this is actually what we call a product set. Product set A cross B of the set A and B is a set, okay, with what? It's a set with elements that are pairs, pair of A, B, okay, where A is in A and B is in B. Okay, so actually you encounter this quite frequently already. What have you encountered? R2. What is R squared? Actually, it's R cross R. Okay, so this is one example you have frequently encountered is like R2. So what's R2? So R2, you know how to draw a plane, right? So you draw a plane. So what's the element here? These are the point on the plane. Right? How do you describe the element here? How do you describe the points in R2? So it's a double X and Y, where X, Y is in R. So in this case, A and B are all real numbers. Does it make sense? Okay, so this is sometimes we write as R cross R. Okay, so this product set is just taking one element from the first set, taking another element from the second set, and then you form a double of elements. And then you can do it for product set of n set, okay, like Rn, right? For example, R3, R4, R5, R6, Rn. R infinity also you can do. So it is a non-stop tuples. Tuples, okay, not tuples, tuples. Does it make sense? Okay. Yeah. So it's nothing. It's just take one element from the first set and then take the element from the second set. Okay. It's a new set. Okay. If you want to think of it as an operation of set, I think you can take two set and then produce another set. Okay. Is it everyone okay with it now? Okay. Okay, good. So before we go into vector space, I still want to talk about ring first because I want to talk about field. So what's a ring and field? So by the way, field here is not the magnetic field. It's a field in the mathematics. So what's a field? So first of all, before we talk about field, let's talk about ring. Okay. So what's a ring? So we upgrade ourselves now. Okay, just now groups only have one law of composition, right? So when we talk about rings, we want to have two law of composition. So just now you have encountered this kind of object, right? A set with two law of composition. What is it? Just now, have you encountered something like this? The non-zero rational, right? I can add them, I can multiply them. Okay. Okay. So of course it's not that easy. So we want to have some more condition to control this ring. First of all, you have two law of composition. We call it an addition and multiplication. Okay, so that's a prototype to a ring. So you should remember when people talk about ring, you should remember integer. Yeah, inside integer you can add, you can multiply. Okay, so keep in your mind that the example of integer. See whether it satisfies what I say later. Now, okay. So you have to satisfy three axiom now. Okay. So what do I want to control? So first of all, I control the LLC first. Sorry, the addition first. Okay. So what do I want the addition to satisfy? So my set should be an abelian group under the addition. Okay. So think about it. Does the integer satisfy this property or not? Is it an abelian group under addition? Okay. With identity, we call it 0. Is it true? Okay. Second, so with multiplication, it has to be associative. Okay, it has to be associative. With multiplicative identity, let's call it 1 in this case. Okay, is it true for integer or not? So not that in this case here, we don't demand commutative here. Okay, we don't demand commutative for multiplication. For a ring, okay, we don't demand that. So the third one is distributive law. Okay, distributive law. So what does distributive law do? So for every 3 elements, what can I do? What do I want to distribute over? So now you have 2 operations, right? 2 operations. So you want to talk about how these 2 operations react with each other. Okay, so what do I mean by that? So for example, what is A plus B times C? What should this be? A plus B is another thing in my ring, right? And then C is another thing in my ring. So I can multiply these 2 things together. But what we can do is we also can do AC and BC first, and then add them together. So this is a distributive law. We demand this to be equal, these 2 things to be equal. And another way is C times A plus B is equals to CA plus CB. Okay. So this is like something, I think what we call last time is open the bracket. Open the bracket. I mean in the high school, like secondary school, at least what I learned. Okay. So this is distributive law. So and then of course you can add commutative multiplication. Then we will call that this ring is a commutative ring. Okay. So we call a ring is commutative ring if it forms an abelian group under multiplication. Okay. So the prototype here you should imagine is prototype example is integer. Okay, the integers. Okay, the integers is the ring. It's a ring. Okay, and so let's go to very interesting definition here. So what's a field is? So a field is a commutative ring. So in our case, we take commutative ring. So let's write it like this with all non-zero elements invertible under the multiplication. Okay, so note that we stress on this all non-zero elements because zero exists in a ring, right? As an additive identity. So it's like just now we already discussed what is 1/0. It's undefined. So we only demand that all the non-zero elements are invertible under multiplication. So what's the example here? What's the example here? What are field? What are the examples here? So you have to have a set with 2 operations. You can add, you can multiply. Right. So under addition, it is abelian. Under multiplication, all the non-zero elements are invertible. Any idea? Pick from numbers. Complex number. Maybe we don't go so far yet first. Can we have a simpler one? Natural numbers. Okay, let's talk about natural number first. You can add. Can you add? You can. But is 0 exists in natural number? No. Okay, so depends. Okay, so some convention we include 0, some convention we don't include 0. But even if you include 0 into your natural numbers, does it form a group under multiplication or no? Or even addition? No, right? There's no negative. If you want to add the negative in, then you will get the integers. And so this is what we call a group completion. Okay, so if you do a group completion of a natural number, you get integers. Okay, so natural number doesn't work because even with addition, it doesn't work already. What else? A bit simpler than complex. Oh, rational, huh? Okay, rational, sure. Okay, let's talk about rational. So rational, you can add, sure. Okay, it's a abelian group under addition, right? And you can multiply rationals, and then under rational is also a abelian group, right? A times B equals to B times A. And all the non-zero elements are invertible. Right, I can take 1 over it. So yes, so rational is a few. What else? Irrational. Irrational. Um, irrational. How to talk about irrational? Huh? Irrational zeros. Okay. Irrational is a bit awkward actually because when we define irrational, we define it either using upper bound property or either using the limit property. But that's the comment I want to make. But so there's no zero there. Okay. To change that, there's no zero there. Okay. What else? Real numbers, yes, real number. This is the physical world you live in. Real numbers. Real numbers. A very important example of field. So the next example is C. Actually, I haven't introduced what is C yet. So C, you can regard it as a R plus IR, such that I shouldn't write like this, so such that where I square is minus 1. Okay. So if you are pedantic, you should ask again, wait, what's the addition between set? I don't want to comment about that one. Okay, so it literally it's just something like all the element is like A plus BI. Okay, such that I square equal to minus 1 and A and B are in. Okay, this is what I meant. Okay. Very intuitive, right? Intuitive? Yeah, should be intuitive. Okay, max should be intuitive. So if you think that max is hard, then something wrong with you. Seriously. Yeah, seriously. I'm not condemning you, but what I want to say here is there's some wrong thinking you are making. Because max should be intuitive. If it is not, then it is not max. Okay. Okay, so we have done this few ring group. So these three things. So you should imagine I'm trying to combine this thing together. Okay, how do I combine this thing together? So let's not go into the axiom first. So I'm going to introduce a very important definition for you. At least for the physics nowadays, it happens in vector space. So what's a vector space? I want to warn you that this definition is not contemporary or classical. So I want to talk about this definition because I want to make the definition of vector space compact. So a vector space V, okay, it should be over something, which is a field. Okay, whenever we talk about vector space, you should tell me what's the scalar. Usually we call this field the scalar for this vector space. Okay, so you need to tell me what's the scalar, okay, on this vector. So how they combine? Okay, how we combine this thing? So it's a set. First of all, a vector space is a set. So last week, someone asked about what is space. For general space, we just mean set, just a set. So now we put an I can say adjective on space is a vector space. So what is a vector space? So first of all, it's a set with a defined operation. We call it a vector addition. And so vector addition just says how we compose two elements in this set. Okay, vector, I take two. So elements in vector space, we call vector. So how to compose two vector? It's through addition. Okay, we call it addition. And then another thing we want is, so should I break this down? So I think it's better to break this down. So first of all, there are two operations here with A, okay, a defined vector space, a vector addition. Second, okay, we call a scalar multiplication. Okay, so what's the scalar multiplication here? So just now I said that the scalar usually we refer to the field, so which is a group action. The field, okay, on V. Okay, so in your mind, you should have a prototype here also, right? R2 or R3 or R, even R. Okay, so there's a prototype here. So R2, so the element are XY, right? And then you can take a scalar multiply to XY. So let's discuss a little bit about so how R2 is a vector space. So what do you do? So if I give you x1, y1, x2, y2, how do you add them together? How do you add them together? You add them component wise. Okay, so you add x1 and x2 together, and then you add y1 and y2 together. So scalar multiplication here means what? So if I give you any scalar, okay, number in R, okay, how does R multiply to any vector? What do you do? Yes, multiply all the components. Okay, you multiply all the components by the same R. Okay. Okay, so it's not just this. So this group action here have to satisfy two properties. So let's return to the definition. We haven't finished yet. So this group action you need to satisfy two properties here. So first, I will call it distributivity over vector addition. And second, you need to distribute over scalar addition. So just now we see that distributivity laws works when we have at least two operations. Okay, they need to react with each other. So let's see what are these two. Let's take some elements from my field, okay, or my scalar, and some element from my vector. Okay, so what can I do? So I can consider two elements here. So what kind of elements I can consider? I can consider a scalar multiply the addition of two vector, or I can consider the addition of two scalar multiply with a vector. So any guess what we have to get here? Any guess? So let's talk about the first one first. So if I take a scalar, multiply the addition of two vectors, have to equals what? Huh? Yes. Yes, the you can do multiplication first or scalar multiplication first, and then you add them together. Okay. And then the next one is you can do scalar multiplication first, and then do vector addition. Right. So the way you talk about it is very important in higher algebra or representation theory. So we want something that commutes. Okay, we can do addition first and then multiply, or we can do multiplication first and addition. It's the same thing. Okay, this is something that what we say commuting. Something is commuting, but I didn't tell you what is it. But in future, if you heard about this thing, maybe you can relate. Okay, so what have I done here? So okay, so this is a vector space. This is the full definition of vector space. So to talk about a vector space, you need to talk about over what field. Okay, and then it is a set that satisfies some property. So in this set, you can add, which we call vector addition. You can multiply, but when you multiply, you don't multiply within the set. You multiply with something outside the set, which we call the field or the scalar. Okay, scalar multiplication. And then this scalar multiplication have to be a group action. So group action just now, still remember two laws, identity laws and associativity laws. Okay? So the one inside the field, when you multiply to a vector, you should get back your vector. And then associativity laws and these two distributivity laws. Okay. So anyone have seen other definition of vector space or not? Did you see definition of vector space in any courses you take? Linear algebra, what have you seen? There are 10, right? So there are 10 of them. So I have it here. There are 10 of them. Right. So if you have U and V in V, U plus V is in V. Group. Right. Closed group. U plus V equals to V plus U. Commute. U plus V plus W equals to U plus V plus W. This is associativity. And then this is object zero, the identity. And then negative U, the inverse. Right. What else? This is if K is any scalar and U is any object, then KU is in V. This is group action. If you have a group and a set combined, you still go into the set. And then this is the distributivity that I introduced just now, these two. And then this one, this one, K multiplied with MU equals to KM times U. What is this? Associativity in the group action. And then the last one is also the group action. Identity law. Okay. So I summarize this 10 axiom using groups, language of groups, group action. Okay, that's all. Yeah. Okay. But it's not quite ring, it's not quite a ring because this multiplication here doesn't happen inside the set. Okay, you have to take something outside. So we use group action. Group action is you take a group and then you add on the set, you get something back inside the set. Does it make sense? Okay, so this is a vector space. This is about vector space. I think I don't want to write down. Okay, so I think you have learned in linear algebra that what are the property of vector space. So vector space, you can check the dimension. How to check dimension? How to find the dimension of a vector space? So you have an idea of linearly independent. So what's the linearly independent means? So the moral of the story is if two vectors is linearly independent, then you cannot produce one from the other. So for example, 1, 1 and 2, 2. Is it linearly independent? No, right? Because 2, 2 equals to 2 times 1, 1. So you can produce 2, 2 from 1, 1. So they are not linearly independent. So we want linearly independent vectors because we are trying to rebuild our vector space. No. Okay. And then the other concept is a span. Do you remember what a span is? Maybe I write span down because maybe it's more easy to. Let me see. So definition. So a set of vectors v1, v2 up to vp in a vector space V spans V. What does it mean by spans V? Okay. If for every non-zero V in V, there exists I think something wrong inside here. Okay, so there exists how should I put it? So there exists non-zero scalar x1, x2, xp, f. There's this non-zero scalar. There's this scalar. Okay, so let me write down what I need first, and then I will adjust this. So such that v equals to x1 v1 plus x2 v2 plus . Okay, so actually I don't require every of them is non-zero. Only it could be zero for finitely many. Okay. But finitely many zero. So meaning if you give me anything inside this V, I can find linear combination using finite subset of this thing. Then it spans. Does it make sense? So it's a bit like surjectivity. Every element in the vector space, I can use this VI to build it. Just using what? Scalar multiplication and vector addition. Two operations only. Scalar multiplication and vector addition. I can build everything inside my V. Then it spans. And then we call that this set of vector spans. Does that make sense? Yeah. It's a bit like surjectivity. Can I reach everything inside my set or not? Okay. If this set span V and linearly independent, then we call this set of vector as basis. Why basis? Basis is what? It's the base, right? You build a house, you need a base. If you have a base, then your house is safe. Right. So basis means you can build your vector space using two operations only: scalar multiplication and vector addition. You can build the whole space. Okay, then this set of vectors will form a basis. So what's the dimension of a vector space? It's the size of this basis is the size. So how many vector you need to use to reconstruct the whole vector space? This is the dimension of your vector space. Here's size of cardinality. Yeah, size is the cardinality. Yeah. Cardinality of the set. Sense? Okay. So a set. Okay. So let me write down. So set of vectors which linearly, which is linearly and span V is a basis for V. Okay, and then the dimension of V is the size or the cardinality, more formally, cardinality of its basis. Okay. Yeah. So for example, what R2? What's the dimension of R2? R2 is a vector space. What's the dimension of R2? 2. Why? Two elements in the basis. So what are the two elements in the basis? What's I and J? R2, just now I said, right, R2 is at the elements of R2 is the tuple, right? So what's the tuples you have? 1, 0, and 0, 1. But can I pick 1, 0, 1, 1 or not? Can. So the basis is not unique. So the basis is not unique. Yeah. The basis is not unique. But the dimension is unique. So this is an invariant of a vector space. It doesn't change. I give you one vector space, it only has one dimension. But it could have different set of bases. And you can do change of basis, right? Change of basis matrix. If you still remember what you learned in linear algebra. The P, right? PB to B prime. Correct. Okay. Yeah, so you can change between bases. So you can think of it like basis as a, how to represent your vector space. So you have different way to represent your vector space. Okay, using different bases. Okay, so dimension. Covered this already. Okay. What else? Okay. So should we talk about this map? Okay, maybe we don't talk about map first. So the next thing I want to talk about is the flow of a vector space. Okay. So given vector space V. So when we talk about vector space, we need to know where my scalar live. Okay, so it's a field. Or the dual. So let me define the dual of a vector space. It's V star of V is the set of all linear map. Okay. So when we talk about dual of a vector space, it's a set of map. Okay, it's a set of linear map. Okay, I haven't told you what is a linear map is. Okay, so let's keep this as a black box first, later I come back to it. So it's a linear map. Okay, such that actually I have this. Okay, so such that for any element in the field and any two element in B such that V star equals to, or the map Okay, so what's this linear map? This linear map is very special. These are the map going from vector space to field. Okay, I give you a vector, you give me a scalar. Okay, or a number, because just now you keep. So when we talk about field, right, you should have example in your mind like real numbers, complex number. I give you a vector, maybe R2. Okay, I need to produce you one number. So this is the map. So this map has to be linear. So what's a linear map means? So when you add on linear combination of vectors, you could first apply the map on vectors and then do the scalar multiplication. Only then you do the vector addition. Okay, you can split it. See, okay, I have a double notation here, so let me change this L to M times L. Okay, wait. Okay. Okay, so from this linear map, you also can see that how nice is the basis. If I can write all my vector as a linear combination of the basis elements, then I only need to know how how the map add on the basis vector. Then it will define for all vectors. Okay, so this is the property of a linear map. Yes. Can we delay or not? Can delay or not? 10 minutes. I want to finish 3 definition of inner space, non-space, and metric space. I promise 10 minutes. Hang on. It's okay. I want to finish it because otherwise I'll drag next week a bit too much. Okay, so this is the dual. So you have a vector space, you can define a dual vector space. Okay, so it's defined for every vector space. So what's this dual vector space here? Is the set. Okay, it's a set of all linear maps. What does this linear map do? It evaluates the vectors. Okay, you can think of it as an evaluation of vectors. It gives you some scalar. Okay, and then this map is linear. Okay, it's linear. Okay, so any question or not up to now about vector space before we jump into a bit more sophisticated space? Sorry? Yes. Yes, this is the. You mean is this a homomorphism? You mean this one? You mean is L is a homomorphism? Yes, it's a homomorphism. Yes. Yeah, I haven't thought about what. Yeah, because for now I don't use yeah, right. I skip. Yeah. Yeah. So if you know about what is a group homomorphism is, this L is a homomorphism. Meaning it's a map that preserves the group structure on both sides. And this is homomorphism. I have it inside my node, but I don't introduce it now because I'm not using it. If you're interested, you can read it inside there. Okay, yeah, it's a group. But in this case here, we talk about linear maps because these two things, I don't just regard it as a group, but I regard it as a vector space. So that's why we use a linear map here. Because group structure is a bit less. But here we have more. Actually, these two things are vector space. Yeah. Okay. Yeah, so actually you can think of it, F actually is a vector space over itself. Over itself. Does that make sense? It's like R is a vector space over R. So it's a vector space over itself. Okay or not? Okay. So let's finish this 3 thing and then we can proceed to Q&A. So maybe a bit late. If you are rushing to go, feel free to leave. So when we study vector space, right? Okay, actually there's a lot of structure already. We can find a basis of it. Basis can describe everything inside my vector space, but we want to put more structure on it. Okay, we want to put, in particular, what we want to put is inner product space. So inner product on my, I change to a, everyone see or not? Okay, inner product space. So we want to prove inner product on the vector space. Okay, so what does this mean? First of all, this is a vector space. So the space refer to vector space. And then inner product is another thing. So what's inner product is? What's inner product to you when you learn linear algebra? What's inner product? Did you remember anything or not about inner product? A vector times another vector, dot product, right? Okay, yeah, sure. Dot product. Okay. Any other things or not? So when you dot together, you get something not in the vector space anymore. You get something, some number. Right. Okay, so in particular, this is a map. Okay. Let's write like this. Angle bracket. V cross V to F. Okay, let's call this a vector space V over F. Okay. Satisfy three property. It satisfies three properties. Three properties. So let me set up this property. So for any V, W, U in V, we need some scalar. Okay, so three property we need to satisfy. So first property is called the positive semi-definite. Okay. And non-degeneracy. Okay, so what does this mean? So this means that if I take two vector, okay, I dot them together, let's say we say dot, okay, inner product them together, this number should be greater or equal to 0. Okay, I don't get something negative. It must be non-negative. With equality, if and only if one of them is 0. 0 vector. Hope I didn't copy the wrong thing. Okay. Sorry, yeah. So something wrong here. So not any two, is you dot with yourself. Okay, you dot with yourself. Okay, not any two. You dot with yourself. V dot V. Okay. Is greater or equal to 0. It's something non-negative. Can be 0. So when is the time you are 0? When you are the 0 vector. That's all. All the other time you have to be positive. Okay, so this is a definition. So second, there's a conjugate symmetry here. Because sometimes our field is a complex number. Right? So we need to introduce this conjugate symmetry. So when you compose when you dot two vectors together, it's equals to the swap of the two vectors and then take the conjugate. Okay. So this is conjugate symmetry. And then third, so there's a bilinearity here. So what's the bilinearity here? So let me put bilinearity first. So we want this map to be linear, okay? But there are two spots here. So what should we do? So we can use V plus W dot with U is equals to V dot with U plus W dot with U. Okay, what else? So let's say if I have a scalar multiple of v dot with w, what can I do? I can pull the scalar out. But I have extra condition here. I need to take conjugate of k, conjugate of the scalar. Okay, so this is a inner product space. So what's the inner product space? So from the name, you have a space. What's this space? This space is a vector space. And then you have the inner product of this space. So what's this inner product is? This inner product is a function, okay, from v cross v to scalar. Satisfy this three property here. Okay. Does it make sense? Okay. In particular, the Rn is the inner product space. I think if you can recall, what's the dot product between two vectors in Rn? That's a formula of it. I can remember or not. Inner product actually tells you what? Distance. Continue. Square root.
Square root and every element and it's very nice.
Oh, you mean the formula? Okay, but I mean, how to say? But what's the use of this inner product? It can tells you the angle between two vectors, right? U dot v equals to the length of u times length of v cos theta. It tells you the angle between two vectors, right? So norm. So we talk about direction. Talk about the length. So let's talk about norm space now. Okay. What's a norm space? So there are three spaces I want to talk about: norm space, inner product space, and matrix space. So let me give you the word first. Later we'll review what is this. Okay. So somehow this inner product has something to do with the length of the vector. Okay, so this is in mathematics we call the norm. Okay, so what's a norm space? So first of all, again, we are interested in vector space. Okay, and then what's the norm space? I need to tell you what is norm is. Or what is a norm? Okay, a norm again is a map. This map is easier now. Okay, it just give you a number. Okay, if you give me a vector. So normally we understand this as a length. So why we say that this is a length function? So let me give you three properties of this. Again, three properties for this norm that need to satisfy. Okay, so let me see. Okay, so first, again, there's some positive definiteness and non-degeneracy here. Okay, so what does this mean? This means that if my vector is not zero, then this norm should be positive. So if you are not zero vector, somehow you are attached with a positive number. Usually we understand this as a length. Length is positive, right? There shouldn't be a negative length, right? If negative, how you measure? Okay. Okay, norm. So first, positive and non-degeneracy. So only zero. Okay, if the norm of something is zero, that means that vector have to be zero. Contrapositive of this segment. Okay, if you found that some norm of some vector is zero, then that vector have to be zero. Second is what we call the positive homogeneity. Okay, so what does this mean? So next, we want to say that this function should be somehow linear again. Okay, so I need to tell you what's the norm of a scalar multiplied with a vector. Okay, what's this? What can I do? I know what norm acting on V as well. So I should be able to just pull out the k, okay, and then multiply with the norm of v. But we require this k to be positive. So we put a modulus on k as well. Okay. And third property is the triangle inequality. Okay, so what's the triangle inequality do here? So for all v plus w, what's the length of v plus w? So we have v and w here. So we also know the length of v and the length of w. How should they related? How should they related? So maybe in the ideal case, I can just compute the length of v and the length of w, right? And then add them together. Maybe they're equal, but now we just require it is less than or equal. Does this remind you something or not? Pythagoras theorem. E square equals to a square plus b square. Right. So a plus b should be greater than, usually is greater than c. Okay. So this is the triangle inequality. Okay, next. Okay, let me introduce metric space. So how about metric space? Okay. So metric here is the mathematical term for distance. Okay, in particular, this metric space is very important for the general relativity here. Or maybe I comment a little bit about it. So metric space is about distance. I give you 2 points in my space. Can you tell me how far they are? Okay, so this is metric. Huh? Yeah. Okay. Yeah, so again, we are interested in, should we fix this? Okay, we don't speak, let's speak from our calculus or analysis generality here. So we don't just define for a vector space. So we define it for just any set. It's a set and a metric. So what's a metric? Again, function. Again, function. Again, so it's a function. So what's this function here? So we call it d because it's a distant function. Is I give you 2 points, you give me some number. Okay, I give you 2 points. Tell me how far are they? Yeah, no? Okay. So again, this have to satisfy 3 properties here. So satisfy 3 properties. That for all points, so for all 3 points inside my metric space, let's call it M here. Okay. So again, distance, right? Is there any negative distance or not? No. Okay, so it has to be greater or equal to 0. Okay, for any 2 points with equalities. Only when you want to guess? When can the distance be 0? They are the same point. S equals to y. Okay, second, symmetry. Symmetry. So if I measure from x to y, should be the same as I measure from y to x. Okay, so it's not a displacement thing. Correct. It's a distance. Third, similarly, it is it satisfies triangle inequality. Okay, triangle inequality. So dxz is less than or equal to dxy plus dyz. Okay, so these are the three definitions you need before we go into Hilbert space. So so I comment here about so how is this metric space related to GR? So GR, okay, so GR work in the universe, right? But somehow I don't know, maybe Yan Ken can comment a little bit. I'm not sure why GR work on something called pseudo-metric. So what's the pseudo-metric? So first positivity here is violated. It means that there are two different points, but they give the distance between them to be zero. So this is where GR works. It works in a pseudo-metric space. Yan Ken, do you want to comment a little bit? Why? I mean, why does it make sense? Like, where's the 2 point in the space that's different, but why we give them a
simple answer is the fact that if you travel at the speed of light, you somehow do not experience, because in GR you include time as one of your dimensions as well. So the passage of time has some meaning in this. So for GR, the set is a manifold, and then for time light lines or curves, they all points will have zero distance from one another. We are constructing this to convey the idea that if you travel at the speed of light, photons, they do not experience the passage of time. And particles, they do not have proper time. Right?
But do they change in position or
they
don't assume not?
They do, yes. So because the spatial part of the coordinate can change, but the time part of the coordinate will also change accordingly, such that the speed of light is observed. So photons travel through space, but they also travel through time, right? Because time is always moving forward. And if you travel at the speed of light, then the speed of light is you cover this distance in space, but you also move forward this much in time.
Okay.
And this is purposely constructed such that if you do it this way, then all the metric definition will have zero distance. A zero distance in the metric space, but the actual physical distance, how many you have, you can still do it. Yes.
Also, you mean the metrics in the, do you call it Minkowski space?
Yeah, Minkowski's flat space. So it's a 4-dimensional manifold if you include the time on top of R3.
So you mean the metric on the Minkowski space, the time is depend on the spatial?
No. So to rephrase it in relativity, the set is your Minkowski space. R3 including time, so it will be the fourth dimension. Then if you define the metric operation on top of it, then photons will travel along points where the distance between them, define this metric distance in that way to be zero.
So can I just simply say that the metric on Minkowski space is the difference between time and spatial distance? Otherwise, because you gain something in T, right? You gain something in space, right? Then how these two cancel with you?
Cancel.
It's not cancel.
It's how you define the dx1.
Yeah. So when you define it, can I understand it as a cancellation?
No, it's not cancellation. No? It's the signature of that metric, right?
Okay. Yeah. Okay, in that case, maybe next time we bring up the metric function for Minkowski space and we try and check it is a pseudo metric. Is it okay? Yeah, maybe we take it as an example. Okay, so before I end this, okay, so what's the relation between these three? So before I end this, so let's talk about relation between these three first. So before I end this, so first you have a vector space, okay, with so let me use another color. We have a vector space with an inner product, right? Okay, then I can go from this inner product space to a norm space. I can use the measurement between two vectors to give me some measurement on one vector. How can I do this? So it's exactly what the just now say the square root square thing. Okay, so how we do this actually? So actually we define the norm of a vector to be square root of, you take inner product between two vectors, between one vectors. Sorry, yeah, okay, so this is the norm. You can check that this satisfies the three properties. And then just through the definition of inner product. And then how you go from here to a vector space, metric space. Okay, how do you tell me between what's the distance between two vectors? Okay, from norm. How do you tell me? You just compute the length of the difference. Okay, you just compute the length of the difference. So you can take the definition of a metric to be the length of V minus W, the norm of V minus W. Or you can take square root of the inner product between V minus W and V minus W. Okay, so this is how we go from a vector space with an inner product to norm space and then to vector space. So this is how important of inner product in the vector space. So that's why you learn this in your linear algebra. Okay, I can talk about the length of one vector through inner product. I can tell you the distance between two vectors using inner product. Yeah, so I think we don't have time to talk about Hilbert space. Let's stop here. And to talk about Hilbert space, we need to explore a little bit inside metric space. Okay, so I think today's content is quite heavy because this content jump across different subject. I mean different topics of this. So what they did here is we have done group theory a little bit, and we have done a little bit of general topology that existed in this university, metric space. Okay, if you are interested, general topology is a ME course. So I think physics student will take it. Is it? Yeah. So if you are interested, you can take it because I'm teaching it. So if you are interested, do a bit of advertisement. Okay. Yeah. Okay. Yeah. Question. Yes. Yeah. Span definition. Yeah. Yeah. Okay, so I'm not sure I phrased this correctly or not. So what I want to say here is you don't need to express your V with all the non-zero. Okay. Yeah. Okay. So what I want to say here is you might not need all the VI to describe your vector. You might not need all the VIs to describe your vector. So it could be that all of them could be non-zero, but it could be finitely of them is zero. If all of them is zero, I mean, wait. So there's something wrong here again. I mean, I think I need to fix this phrase here. But what I meant is you don't necessarily need all the VIs to express your V using scalar multiplication and vector addition. I think I need to fix the phrase here. I think something wrong here. Yeah, because if finitely many, then if my set is finite, then it could be all zero, then something wrong again. Yeah. Okay. Yeah, I will fix the phrase here, but what I want to say is for every vector you don't necessarily need all the vectors to express it.
They just say some of the I can be zero.
There's this some non-zero. There's this some non-zero.
No, I mean, say somebody one.
Because when we talk some of them, then maybe all will happen. Zero. Yeah, zero better because but now I fixed this definition to non-zero V only. So not all zero. Not all zero. Not all zero. Some zero, but no. Some zero, but no. Some zero, but no. Yeah, some zero dot but no. I think works. Some zero. Okay. Yeah. So I think let's fix this. So this one change to some zero, but no. I think this is correct. Some zero, but no. Yeah. Yes. Thank you. Okay. For this one. Some zero, but no. Yeah. I think this one correct. Okay. Good. Any other question or not before we end this? No. You have something to say or not? Yes, before. Okay. Oh, yes.
A question inner product space, right?
Mhm.
There are three property that we have to satisfy, which is the one is the bilinearity. I don't get why do we need to get the conjugate of that thing.
This thing have to do with the conjugate symmetry. There's some convention that if I do VKW, then maybe there you need to do conjugation when you put it out. So this have to do with this conjugate symmetry. This is what can I prove this? I mean, maybe not now, but okay, next time. Okay, so next time. So I mean, this is not to violate the conjugate symmetry, the purpose of this. But there are two conventions of doing this. I just picked this one. Yeah, it could be that V dot with KW, that when you put it out, you need conjugation. Then the other you don't need. I mean, this is a choice so that 2 is satisfied. This is just a choice such that 2 is satisfied. Yeah. Okay. Otherwise, if you just put it out without conjugation, then something will get wrong with this conjugate, the second property here. Yes. Yes. Uh-huh. Uh-huh. Yes. For example, in real number, there's no conjugation. No? But in the complex, the conjugation is the A plus BI become A minus BI. I could define for different field, probably, like the Hamiltonian. Have you heard of Hamiltonian number or not? Octonian number or not? No? Yeah, it's because like for example, okay, I mean, have you heard about IJK or not? I square, J square, K square equals to -1. That's the Hamiltonian. Octonian you have. Sorry? Oh, Quaternion, sorry. Because I remember I use H. Wait, Q. Did you use H or just use Q? Yeah, BH. I thought it's Hamiltonian. Yeah, Quaternions, yeah. Does it have different name or not? I forgot. But it's the Quaternion and then Octonian, then probably there's conjugation there. Yeah. Any other question before we break? Okay. So yeah. So if you have more question, you can bring on next week, and hopefully the plan for next week should be finish off with proof of generalized Heisenberg uncertainty. Okay, so basically is the uncertainty between operators. Okay, not just position and momentum, but in general, operators will have this discrepancy. Okay. So we end. Okay, so thank you for open question, right? No question already. What?
So basically, for the lecture just now, right? We Dr. Ni already defined action, right? And in quantum mechanics, normally we do, let me write it down. So normally in this is an operator, right? For kissing this is poly Z matrix. Okay, so this is let me write it down. So the result actually is can you guys guess? I think the answer is already there, right? I think the answer is there, right? About the action of a group.
I mean, it's a 2 by 2 matrix, right? So you need to multiply a 2 by 1 matrix.
Oh, okay, maybe let me prove it.
So what's the vector? I mean,
It's the language of
Yeah.
today.
Yeah.
The vectors.
Yeah, just use the language of today.
Two-dimensional
Yeah. To mention this, it's actually just to mention to remind the physics student. Actually, we do this every day, but that is just the actions. Actually, what we do. That's the things I want to mention. So yeah. And
okay, I think let me add something to this. So I mean, all right, okay. So you have a operator, sure, okay, a linear map on the vector space, right? This is the vector space, right? Inside a vector space. Okay. So just now you can also talk about this is a complex two-dimensional vector space. So this is a vector space over C. Okay, so this is the field C with dimension 2. So the dimension is 2 means what? There are 2 elements inside your basis. So you should be able to write it down. What's this thing? What's this vector here? So do you mean this is 1, 0 or 0, 1? Or 1, 0. Yeah. So if you give me this, then of course I can compute this for you. Right. So it's a 2 by 2 matrix with a vector. I can do matrix vector multiplication. But this doesn't make sense with this thing. Right. You get what I mean? Yeah, so you need to like write down what's the mathematical definition. So this is defined like this, is it? Or is a choice? I don't know. It's defined like that. Okay. Because like what I said just now, you could pick different bases. I think in particular, I think your professor, I think Thomas, actually, I think he frequently raised a question in several physics seminar that what if I change bases of the vector space? What happened to this polymatrices or something like that? Even this polymatrices form a base for some 2 by 2. I mean, not 2 by 2. I mean, R4. Okay. And if you notice, what's the determinant of this matrix? What's the determinant? -1, which is not 0. Which means this vector is, this matrix is invertible. Okay, so it's an element of GRN. Okay. Yeah. Okay. I think you want to bring up the idea that this is a group action, right? Yeah. Group action on the vector space. Can I change the 10 to 11? I think they define.
Sigma y, sigma x.
No, you mean the cat? Can they change to 10 instead of change to 11?
What's the other basis here? Down.
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 Yeah.
Down defined as
0, 1.
0, 1.
Up.
Up.
Yeah.
Yeah. I know. Yeah, I know. So I mean, this is the preferred basis, standard basis. Yeah, standard basis. I mean, I think I think his idea is like, can I put 1 for up?
I mean, yeah, it's in QM notation, right?
Any meaning for up and down?
Yeah.
Spin up, spin
In
down.
QM notation, the standard notation is 1 0, then 0 1. So and then the polarization basis will be 1 over √2 because you want to keep them norm 1 up. So yeah. Right. So if you work this out, it's gonna be 1 over √2. That's 1 1 and plus and minus 1, right? So yeah, you this is a different basis, right? And then so you can no, I think that's a different thing. It is a no, it's a different basis because you can so this is the eigenstate of the I think sigma x or sigma y operator. Right. So yeah, if you try operate sigma x onto it, then I don't know if anyone because we didn't define sigma x. Right.
So seems like there are physical meaning for the standard basis and this kind of basis, right? But there's like I think infinitely many bases here. So does all of them or some of them have physical meaning? Or not
I
sure.
would say okay. I would
Must exist or not? Maybe
I
haven't
mean,
found.
definitely
Yeah. Yeah.
basis exists, but
Yeah.
But to keep track of everything, right? We just start with the convention that spin 1 you can imagine a particle with angular momentum component pointing in the z direction, right? And if you start as this starting point and then using the symmetry group that it it obeys, then you find that there are uh, 3 Pauli matrices, right? And then from this, each of these are linear operators. Like linear algebra, they have their eigenvectors and everything. And then you can transform between one of them. So starting from there, you can transform into like different independent basis, and that would be the useful one. Of course, you can like transform into any arbitrary basis, but to then there might be already overlap with the original one, so there's no point to consider that. Right. Yeah, something like that. I also can't forget. It's been a long time since I done this.
So like this, any preference like when we want to consider the up down or when we consider plus minus?
Normally yes, because normally normally in practice you have up down and then you want to transform to this is because the eigenstate of one no sorry these are eigenstates of sigma z, right? Then you transform to this, they are no longer eigenstates. And in quantum mechanics, you are interested in finding states that are not eigenstate of some operator because that is where you get all the quantum effects, right? Like the superposition and things like that. So, and then that is like the nicest, that is like the most, 45 degrees, right? You transform your basis by 45 degrees. So it's like a nice, right in the middle of everything. So you just focus on that part.
So does the 45 degree have to do with the time con or not?
No, this quantum mechanics. It's not.
I know quantum mechanics, but if you want to combine quantum and
no, this is not position and time, right? It's just the spin.
Test.
Yes, all right. I think that's all for today. Before we end our seminar, right, I would like to comment one thing. This seminar, right, is actually just a personal talk. When I mean this kind of thing is just my communication with Dr. Ni is just in his lecture room, no, in his office. So in the future, right, so any one of you, even like you and your friends or you and your lecturer, you guys are interested in any topics, welcome to Teams Me so we can organize more event like this. So all the ideas are come from discussions and all the answers come from your discussions, right? So never stop asking questions. Okay. Right. Thank you.